So yeah, thank you, Maria. Thank you for all the nice introductions to the school and all the great things that were said about machine learning. Hopefully, you won't all be incredibly disappointed when you start using and experimenting with machine learning after all of that hype and all of the things people have been saying about machine learning in the press and what have you. So as was mentioned just a few seconds ago, I'm Charles Parker. I'm the Vice President of Machine Learning Algorithms at BigML. And this talk that I'm going to give is going to be mainly just kind of an introduction to get us all on the same page. It might be a review for those of you who have already heard about machine learning and are already familiar with some of the basic concepts. Some of them might be review. But the idea is, again, to just give a basic introduction to machine learning, and especially to talk about the different ways in which machine learning can be used, and especially maybe some of the ways in which machine learning shouldn't be used. So to approach a use case for machine learning and have some rubric in your head for saying, all right, this is a good problem for machine learning. This is something we should attack with machine learning. Or maybe this isn't the right problem to attack with machine learning. Maybe there are good reasons to believe that something else would work better. And so that's a lot of what I'm going to talk about in this talk. And so it'll be a little bit short on technical details. I'll gloss over a lot of things in the name of kind of just talking about how machine learning is used and how we think about machine learning kind of before we begin to actually do it. So as I was saying, there will be a simple introduction to supervised machine learning. So kind of one of the most common use cases with machine learning. And then as I'm doing this, I'll also introduce the BigML platform because we're going to be seeing that a lot. And so I'll just introduce some of the core concepts within the BigML platform, how we create resources and what resources are in the BigML platform. And then kind of the bulk of the talk is going to be how to tell whether or not you have a machine learning problem. So you have some data sitting in front of you. You have a problem you want to solve with that data. Should you use machine learning to solve it? And then at the very end, we'll give you kind of a little preview of the next few talks. So we'll take a tiny peek behind the curtain to see what some of that technical detail looks like as we start to actually do machine learning. So just as a motivating example here, imagine you are the CEO of a mobile phone company. Congratulations, I know you worked very hard to become the CEO of a mobile phone company. And one of the problems you have as the CEO of a mobile phone company is that people leave the service, right? At the end of every month, you have this customer churn, they call it, right? People will leave the service at the end of the month. And thankfully, as the CEO, you have a budget so that you can reach out to some people at the end of the month who you think might leave the service, and you can give them some incentive to stay, right? You can say, oh, I'll give you this promotional rate if you stay with the service, or we'll give you some free phone or whatever. You have some incentive to try to keep them with the service. Of course, to do that, you only want to reach out to the people who might be leaving, right? You have only so many hours in the day. You have only so many operators who can work the phones. And so you need to identify a subset of your customers who you think might leave the service next month. And so to kind of get very specific here, suppose you can identify 10,000 customers. Suppose you have an existing strategy that identifies 10,000 customers that you think might be leaving the service next month. For every 5 people you call, let's say 2 are actually thinking about leaving the service. So your existing targeting strategy for these has a precision of about 40%. Just to put some kind of random numbers on this thing. And then of those customers, your operators can convince half not to leave the service. So by incentives or just kind of cajoling or resolving some difficulties they have, your operators are able to convince half of those people not to leave the service. And if you have some kind of estimated value for those customers, let's say $500, then you know how much money this effort is making you, right? And in addition, you know that if you increase the precision of your targeting to 50%, you know exactly how much money that's going to make you, right? It's going to make you an additional 20% on top of what you have there. So I think that's, your existing targeting strategy is 2,000 times $500 is like $1 million it's making you, so it's making you 20% above that, another 200 grand. So you have a precise number about how much this machine learning effort would make you. So if you can increase the precision of your targeting to 50%, that's worth $200,000 to you. This is like a very important exercise to go through when you're thinking about a machine learning problem, is exactly the dollar amount that this is going to make you. You want to estimate that as precisely as possible. Because if you don't, if you just say, oh, I want to increase the precision of my targeting strategy, I'm going to use data, then you have no idea how much that's worth to you, right? And these machine learning projects can get very expensive. It seems like, oh, everything is automated, this is going to happen by itself. You know, we're using machine learning to kind of automate this, and so it's very, it's cheap. It doesn't require labor. But in fact, setting up the process and going through and iterating all of these models tends to require a lot of human labor. You'll need engineers. You'll need to clean the data. You'll need some expertise in machine learning. So there is money associated with this effort. And just going into it thinking, oh, we're going to use machine learning to solve this problem is almost never enough. And finding a way to put a dollar amount on exactly, not just we want this machine learning project to make us $200,000, but if we increase the existing accuracy by X%, that's going to buy us X dollars. That's going to get us X amount of profit. To have something that specific in place is really essential, especially to convincing people in upper management that machine learning is a good idea. And then it also gives you something to deliver, right? Then you know you've succeeded or not in very concrete terms. So here's some data for this problem I was just talking about. So this is manufactured data. This is not real, but it's the sort of thing you might get if you were trying to solve this churn problem. So these are, for each customer, for each month, you have attributes of how they use the service in that month. So the top row there represents some person in some month. They used 104 minutes on their mobile phone plan. It was, you know, their last month's bill was $103. They didn't call support, they didn't visit the company website, and they didn't leave the service at the end of the month. And each row in that table represents a person in a month. And so then this is kind of where the magic happens, right? We can use this data to kind of automatically create a better targeting strategy. Once we have the strategy in place, we can use the data to automatically create it. And we'll get to exactly what that means in the next few days. And then we can also use that very self-same data to measure the effectiveness of that strategy. So in the last slide, or in a couple slides ago, when I said we're going to increase the precision of our targeting strategy to 50%, and that's going to, you know, raise our bottom line by X amount of dollars, you can use the data to estimate exactly how much precision you're going to buy with the machine learning strategy. So that's the nice thing about machine learning, is it provides you with kind of instant feedback if you do it correctly. You can use the same data that you use to train the model. If you do all your splitting and holdout sets and all that stuff appropriately, you can use this very same type of data to measure the model's performance. Okay, so kind of switching gears a little bit, I actually have a CSV with that data in it, and it is right here. So here's that same data. This is just a CSV file that you could open in any spreadsheet editor or text editor or whatever. This is the same data. I've just got more of it. I just made a few thousand kind of rows of this data. And this is just a CSV file that sits on my desktop here. And so I'll close it and get rid of this display stuff. And so I've got BigML open here, and to feed the data into BigML, I can just drag my CSV file. File type, no, oh, that was actually, yeah. So I accidentally put the presentation in there. Obviously, I don't want to analyze my presentation. Who knows what would come out of that? But yeah, the CSV file is now my BigML source here. So my data is in the service. And you'll note as you start to work with BigML that everything you create on BigML is called a resource. So basically, when you're working with BigML, you're just creating resources. That's what you're doing. And the things you need to know kind of about all resources, anything that you make on the platform, first of all, they're mostly immutable, which means you can't change them, which means you can't screw them up. So if you learn a model and then you want to try something else, learn a different model, use different training data, blah, 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 the model that you created initially, it always exists. It's always sitting out there in the form that you originally created. You can't change it, you can't mess it up. It's always sitting there. You can always go back to it. So this is what we mean in BigML when we say, part of what we mean in BigML when we say that when you do analysis in BigML, it's traceable, it's repeatable. It's part of that is that these resources can't be changed, right? So you do some analysis, the results of that analysis are there forever unless you explicitly delete them. You never lose anything in BigML. They're assigned a unique ID, so you can always go back to that thing you created, whatever that thing you created is. And you can always access both programmatically via the API, via Python or curl or whatever. You can always do it via the API, or you can do it via the UI. So everything is present. Everything you create in one place is present in the other place. If you create it programmatically, you can still look at it in the UI. If you create it in the UI, you can still access it programmatically. And as I said before, working with BigML is a process of creating these resources. So every time you do almost anything in BigML, you create a new resource. And so you can see here, this is the resource I just created, this data source that I dragged into the platform. When I drag data into the platform, it becomes a source resource. And so what else? So sources at BigML, data source, is basically a representation of these raw files that you brought into the platform. So that's the thing I just created when I dragged the CSV into the platform. What do we do when we make a data source? We make some guesses about how many rows and columns. We look at basically the first few rows of your data set, try to figure out how many columns there are there, what type they are, whether or not they're numeric or a date or something like that. We try to guess the language of the text fields that are in the data. And the data can come from kind of anywhere. So if we go up here, you can create a source inline just by typing it into an editor like this, or you can create a source from just a URL on the web, or there's a number of services. You can do Dropbox or Google or what have you. And then if I click on the source, you can see that it's found the 5 columns in the source, minutes used, last month's bill. It's been able to guess the types of those columns. And so all this happens automatically. Like no matter if you have CSVs in a different format, if the separator is a semicolon or something, or if your numbers are in a different format, you have a comma as the decimal separator. We try to do all of this automatically as well. And then the next thing you do after you have a data source is you create a data set. And what a data set is basically we're going to make a pass through all of the data in that data source, and we're going to kind of finalize our estimation of what the columns are, what languages for text fields we have, what the formats of different numbers are, and also we'll collect some summary stats about each of these fields. So I'll just do that so you can see it. You can go up here. The Cloud Action menu up there gives you all of the things you can do in one click from this resource. So again, I'm going to create another resource, right? This is what I do when I work with BigML. I have a resource. I use it to create another resource. In this case, I have a source. I have a raw data file, and I'm going to use it to create a BigML data set. And so one-click data set, and it'll take no time at all. And you can see here that we've made a little histogram of all of the values in the data set for variables that are categorical, like churn, can only be no or yes. Here we've got a little histogram of those values. So this is what we do when we create a data set. And also behind the scenes, making that initial pass over the data set allows us to serialize the whole thing into a very nice format that's fast to read, so that when we create things from this data set, different models on this data set, we can do that way more quickly than we would be able to just working with the raw data. And so you see right away from this data set, like just by creating the data set and collecting these statistics here, we have a few things that we can say about the data set, right? So here, most people don't leave the service at the end of the month, which as the CEO is good news for you. You want people to stay with the service. And that happens. About 90% of the time, people don't leave. And then the remaining kind of smallish percent of the time people leave the service. And similarly, you can see here that, again, most people don't call support in a given month. And then there's kind of this tail of the distribution where people call support a number of times during the month. OK, so that's the data we have for this little toy problem, for this little toy churn problem. And again, what we're going to try to do with this data is we're going to try to use it to build something. So the process of doing this is we're going to collect this training data from the past, right? We have many past months of customer churn data, many months in which some customers did leave the service, some customers did not. We know about their bill from those months. We know how many times they called support from those months. We have all this data from the past, and importantly, it has the right answer in it, right? From all of the months in the past, we know, I bet that's for me. From all of the months in the past, we know if they left the service at the end of that month or not, right? So we know the answer to our prediction problem for the data in the past. And that's very important, right? This is what supervised machine learning is you give it the right answer, and that's how it learns to make the prediction, because it's seen the right answer so many times. And so this is the kind of data that we have. And we're going to feed that into a machine learning algorithm. And the algorithm is going to look at the data. It's going to look at the right answers associated with those previous rows in the data. And it's going to use that to create a computer program that we usually call like a model or a classifier, but it's basically a computer program that will make that prediction for you on future data. So in future months, when you don't know the right answer, obviously you don't know if they're going to leave the service at the end of the month, you can use that model to kind of guess, right, to make a prediction on whether or not they're going to leave the service. Because it's seen so many other months in the past, it knows how to do that. And so, again, that seems like magic. It seems like it's just looking into a crystal ball, but it's really basically just statistics. So popping up the stack, kind of one level here. What's a good way to think about this? You know, again, this seems like magic, right? We have all this past data. We're going to feed it into this algorithm, and it's going to magically produce this predictor for us. That seems like it really has no precedent. But in fact, there is a pretty good precedent for this, and it's kind of traditional expert systems. So in the past, if you wanted a system that automatically predicted whether or not a customer was going to leave the service, you would engage two people. You would engage an expert and a programmer. And it would be the job of the expert to sit down with the programmer and say, OK, here's what I know about people who leave the service. I'm an expert in this data. I've been working in telecom for 20 years or whatever. I know what the signs are when people are going to leave the service. They call support. They've had a big bill recently. And you know, they're visiting the company website all the time trying to find answers. That's how you know somebody's going to leave the service. And that person sits down with a programmer, and the programmer says, OK, I'll encode that knowledge into a computer program. And then when somebody wants to decide when someone's going to leave the service, they'll use this program that I've built, the programmer. So you have these two people, right? You have the expert, the knowledge about the domain. And then you have the programmer, the person who can encode that knowledge into a computer program that will make the prediction. Sometimes these are the same person, right? Sometimes the expert is also a programmer, and so they can encode their own knowledge into a program, and that's the way you get the expert system. But you need both. You need the expertise, and you need the ability to encode that expertise into a computer program. If you don't have one or the other, then you can't do it this way. And so now, with machine learning, we're basically doing the same thing, except instead of having an expert and a programmer, we have this data, and we have an algorithm that can work with the data. So what's the advantage of using data over a human expert? First of all, data can be easier to get. You know, humans are finite. When you're an expert, you're just somebody who can't be more than one person. But data can be replicated, can be distributed all over the world. So data can be easier to get at than a human expert. And in some cases, there really isn't a great human expert, but the data is already there. And also, typically, you can get a volume of data that's much larger, or not typically, but in many cases, you can get volumes of data that are much larger than any human expert would ever see. So a doctor who is trying to do medical diagnosis, he might see hundreds or thousands of the same type of case, right? He might see hundreds or thousands of people with diabetes, and that's what he's basing his expertise off of. With data, we can get orders of magnitude more, right? We can get hundreds of thousands of cases. We can get millions of cases. So the algorithm gets to see a lot more cases than the human could ever possibly look at. And then the last kind of advantage that data has over experts is that experts can be notoriously bad at being experts. So if you're an expert at something, you're still a human being, right? You're still subject to all sorts of biases and confirmation bias and recency bias and all the little psychological tricks our minds play on us to make us bad at actually understanding facts, right? These are all very well known in psychology, is that humans have a whole bunch of blind spots. Data also has blind spots, but those blind spots are a bit different. And so data, again, brings a different set of weaknesses than a human does. They both have different sorts of weaknesses, but it's not like a human is this perfect reasoning engine, right? A human has just as many blind spots as a computer will. And then instead of a programmer, we now have the learning algorithm. So it's the job of the learning algorithm, again, to take in the data, to take in the expertise, and feed out a computer program that has that expertise encoded into it somehow. What's the advantage of using a programmer, or an algorithm rather, instead of a human programmer? First of all, once you have the data in the proper format, human algorithms rather work much faster than human programmers. So you can have a model in seconds or minutes rather than days or weeks. And the nice thing about this is that it enables you to iterate. So if you have some data and you learn a model with it, and that model is inadequate, you can immediately go back to the drawing board and try to find new data or try to use a different algorithm, right? You don't have to wait weeks for the programmer to come up with something before you can evaluate it and decide that it sucks. You can immediately get that feedback. And the other nice thing about this is that learning algorithms are modular. So in the sense that if you have a learning algorithm and it's working reasonably well, and then somebody comes out with a new learning algorithm that's really good, you don't have to fire your existing learning algorithm and provide them with a severance package and make sure their family is doing okay. You can just stop using that algorithm that you have and put in the new one. So where am I going with this? Yeah. So back to the data. So again, as I said in the previous, how am I doing on time here? Okay, that's not too bad. So back to the data. Like I said in the previous couple of slides, the data has to have a particular format, right? Once you have the data in this format, machine learning is reasonably straightforward. Once you have data that looks just like this, that's nice and clean and well formatted, and all the features have the appropriate meanings and are not missing values and so on and so forth. There's a lot. We'll talk about feature engineering in the next few talks. But as long as your data is nice and clean like this, you can do machine learning on it without too many problems. So what do we mean by nice and clean like this at the highest level? Well, first of all, you have to have row-column data, right? This data has rows in it, and it also has columns in it. This sort of tabular data is the usual data we work with in machine learning. Even when you're doing computer vision and you have images, really you're still looking at rows and columns. Each image is a row, and the class for that image is a column. And so the rows in your data, conceptually, we call these instances or sometimes data points. These are some entity about which we want to make a prediction. So in churn prediction, we want to make a prediction about each person for each month, right? Each month we want to make a new prediction about whether or not that person's going to leave the service. So each row in the data set represents a person in a given month. Medical diagnosis, just going through some different domains here, medical diagnosis is going to be a patient at a particular moment in time, right? So you're going to have some patient who comes in, they may or may not have some disease, they have some attributes associated with them, but those attributes are going to be different if you see them again 20 years from now. So they might show up in your data set again at some point, which has its own set of problems, but that's not entirely the wrong thing. Medical diagnosis happens for a given person at a given moment. And so that's what each row in the data set is a person at a given moment. If you're trying to predict the price in the stock market, maybe you're trying to predict the closing price for that day, and so each row represents a day in the stock market. Credit card fraud, you're trying to predict whether or not each transaction is fraudulent, so each row is going to be a single transaction. And then the columns in the data set represent something we know about each row, some information that's going to help us make a prediction. So in churn prediction, the columns we have are things about that customer in that month. The number of minutes they use the service, the calls to support, and so on and so forth. If you're doing medical diagnosis, the columns in the data are going to be something about each person at a given time. So what was their BMI when you tested them? What was their body temperature? You know, various other test results. If you're doing stock market prices, again, the columns in the data are going to be something about that day. What's the previous 5 days trend? The previous 5 days trend is something that's conditional on that day, right? If you, on a given day, you can always measure the trend for the previous 5 days. So the trend for the previous 5 days is an attribute of that day. You know, the previous days open and close, and you know, various, I don't know, volume on that day, so on and so forth for stock market price prediction. And then for credit card fraud, you know, you might want to know about other recent transactions. You might want to know about the amount of the transaction or the geolocation. So where was that transaction made? If your customer is in the United States and you see a bunch of transactions in Japan, you probably know that something is amiss. And then finally, one of the columns in the data set in the supervised learning setting, one of the columns in the data set is going to be the objective column. So it's going to be the thing that we finally want to predict. In customer churn, the thing that we want to predict is whether or not they're going to leave the service at the end of the month. In credit card fraud, it's whether or not the transaction is fraudulent. Medical diagnosis, whether or not the person has the disease. And market price prediction is going to be the price that you're trying to predict. So again, this is just another one of the columns in the data set, but it's going to be the one you don't know when you're actually using the model. It's going to be the one you want to try to figure out. You want the model to try to figure out. And then again, circling all the way back, the goal here is the program that predicts. So you feed data of this sort into the learning algorithm, and it spits out this model. And what's the model going to do? It's going to take a single row of the same shape that as the training data set that you fed in. So it's going to take a single row, like a single person with a certain BMI and a certain body temperature and certain test results. And it's going to try to guess that last column, the objective column, using the ones that you provide. And kind of the most important thing here is that the row can contain any values for the given columns. So the person who comes in will probably have a BMI and a body temperature and test results that your model hasn't ever seen before. It hasn't seen exactly those things in the training data. The model wouldn't be really useful if it only operated on exactly the things it saw in the training data. The whole power of machine learning is that it's able to generalize a little bit from the training data that you have to various other people who might come in, you know, drawn from the same distribution. So people who have test results consistent with diabetes will also have diabetes. Okay, and so kind of as promised, I want to talk a little bit about when it's a good idea to do machine learning. So when I was a grad student, for example, and I first started to hear about this, this was very exciting, right? It seems like a whole bunch of human knowledge can be encoded in this way, and we can develop programs that will kind of have that knowledge embedded in them quite easily, right? But it turns out, of course, that like any powerful thing, there's places where it just doesn't work. So one way that I try to think about it is, again, from that perspective of expert systems. So remember, machine learning kind of replaces these traditional expert systems where you took two people, an expert and a programmer, and got them to build it for you instead of using the data in the algorithm. So to have a successful application of machine learning, you have to have some way that it's better than that. So you have to have either the expert or the programmer has to be either unable to do the job or can't be able to do the job fast enough. And we'll talk about what that looks like in a second. And then also on the other side of the coin, we have to have adequate data, and we have to have an algorithm that can take that data and provide the model that, that gives sufficient performance on the problem. And so, yeah, so some of the spaces that this is true. First of all, performance critical optimization. So there was a recent, so churn prediction, the example we've been using is actually a good example of this. So we can get a human to kind of develop a targeting system that has some performance. But when kind of nominal increases in accuracy, like 5% increase in accuracy, 10% increase in accuracy, when kind of those small differences mean millions or tens of millions of dollars to a company, that's a good place to employ machine learning, right? Where nominal increases in accuracy result in big gains monetarily. So churn prediction, credit card fraud, if you can do even a little bit better in credit card fraud, you can maybe save tens, hundreds, millions of dollars in fraud. Market trading. So I worked in the stock markets for 3 or 4 years as a quant, and if we could get models that were 52% accurate, 53% accurate on binary problems, so things that were just a little bit better than chance, those could make us millions of dollars. And then there was another article about wind farm optimization. Again, this is a problem that people have been doing by hand, making sure that all of the turbines are facing the right way and placed appropriately and so on. This is something we can do as humans, but you use machine learning, you use statistics, you can get 10% increases, 20% increases in efficiency, and ultimately that means kind of a lot of money for the people who are operating these wind farms. So another kind of different sort of case is the case where people can't tell you how they do it. So this is the case where the expert is broken, right? You don't have, the expert isn't able to tell the programmer exactly how they do this thing. And so a lot of these signal processing applications of machine learning fall under this heading. So text recognition, like if I show you a letter A, you will look at it and say, oh yeah, that's an A. And I'll say, how do you know? And you'll say, well, there's like a curve up here, and it comes down this way. And there'll be kind of these vague, even if I draw A's of very different shapes, you'll always be able to tell it's an A, but you won't be able to tell me exactly why in a way that I could write into a computer program. On the other hand, we can feed in millions and millions of A's into the computer program, and it will be able to make its own rules about when something is or is not an A without too much difficulty. So that's a pretty clear application of machine learning where there is no proper expert. Speech recognition is another one. As I'm talking to you, if you know English, you can understand what I'm saying, but you don't know exactly how you understand what I'm saying, right? You could write down every word that I'm saying, but like how does that information translate from audio signals into these words on paper? There's no good expert for that. But again, this is something where we can provide a system with a whole bunch of data and it can just figure it out. Music genre classification. Again, something that computers are very good at if you feed them all the data, but something that we can't really explain exactly why. Oh, I hear a violin and there's a cello and then I hear a timpani every once in a while, and so it's definitely classical music. Like that's, again, something that's difficult to program into a computer. Face recognition, yet another thing you can't explain exactly how you know it's the same person, but you know it is. And then, I'll skip that. But yeah, sort of various natural language understanding things. It can be very difficult to explain exactly why you know something means something else, or why you know that a given document is from a given topic. Oh, it contains this word, but it doesn't contain this word, and it does contain this word. You can't make a general rule. You just look at a single document and you can say, oh, this is about politics because X, Y, Z. So then the other kind of version of this case where the expert is broken is where the experts are rare or slow or expensive. And so medical diagnosis is a good example of this. There's only so many people qualified to read an MRI. You can have a machine learning win by taking all of the MRI data. You can provide an expert in the form of a machine learning system that might not even be as good as a doctor reading this, but it's better than nothing. And nothing is the case you're left with in a lot of situations, in a lot of places where they don't have access to a doctor or where a doctor is very expensive. You can provide something that's better than not a doctor. Autonomous helicopter piloting, this is pretty well documented that flying around little model helicopters, you can do all sorts of crazy stuff with machine learning that humans have a whole lot of trouble doing, or it takes a long time for them to train themselves to do these crazy helicopter maneuvers. Game playing at extremely high levels, so we already know that computers are destroying humans at chess and AlphaGo. This is, again, something where with chess, there's only a handful of top experts in the world, but with loads of data, you can make something that's just as good as those experts, and you don't need access to the experts to build that thing. And then when I was a student at Oregon State, and I think this problem even continues to be worked on today, we had a program to monitor the health of an ecosystem, the health of a forest. And part of this is that we'd get together a whole bunch of dead bugs. We'd get a bug trap in the forest, and we would collect a whole bunch of dead bugs. And then we had to have a count of each type of bug, like how many of these there were, how many of those there were, how many of those. We had to have a count of all the different types of bug, which required an entomologist to go through and look at each of these hundreds of dead bugs and mark it in a spreadsheet. But the people working on this project were able to develop a system where the bug was kind of automatically moved into a little area where it was photographed from a bunch of different angles, and the machine learning system was able to classify the bug and then move on to the next one. And so this is a case where the expert wasn't particularly inaccessible or expensive, but the expert was very slow, right? The expert had to take the bug and mark it into a spreadsheet. Once we had this little system, and the system was kind of cool, it had little vacuums and everything that would just shoot the bug into this area and then shoot the bug out. It happened in a matter of minutes, something that would take days for an expert to do. And then the last little part here where kind of, this is kind of where the programmer tends to be inadequate, is where everyone needs their own algorithm. So if we're doing something like using machine learning to customize a user interface, we're trying to predict what you might do next in the user interface. A lot of times the model you have to build to do something like that is customer dependent, right? If I do 5 things, even if I do the same 5 things as somebody else, the thing that I do next might be different from the thing that they do next, because we have sort of different ways of using the interface. And so it can be advantageous in those situations to build everybody their own separate machine learning model, which is something you obviously can't do as a programmer, because you're not going to go to your millions of customers and hand code a model for each one of them. Various things, if you want to do something with people's mobile phone data, that also often falls into this category where, let's say you want to predict their location, you want to predict like if they're going to work on that day and at what time they're going to work, so you can give a traffic report or something like that. That's something that's very particular to each person, right? Because each person goes to work at a different place, at a different hour of the day, and so each person needs their own little model. Okay, and then the flip side of this, when is this a bad idea, is when those 2 cases that I was talking about before basically apply very well. So if you can build an expert system, or if there already is an expert system in place that works very well, it's going to be hard for machine learning to win. Printer defect detection, when I was working at Kodak, we had these huge industrial printers, and we designed a prototype system that would basically, as the paper was flying by, and they would use hundreds of meters of paper per second, we had a camera set up so that it would look down at the image as it was being printed, and it would decide whether or not the image was defective. And if it was defective, it would stop the press and let the operator do some maintenance or whatever. This worked very well. It was very easy to use computer vision to identify defects in the prints and stop the press. But it turned out that a human, it's easy for a human every few minutes to just look at what's coming off and decide whether or not it's good. And the additional speed gained by using a computer to do that, it did save them kilometers of paper to have the computer constantly monitoring it, but it turned out that a kilometer of paper was only worth a few dollars, so it wasn't really worth it. You weren't really saving anything by having this elaborate machine learning system in there. The human system on a dollar basis was just as good as the machine learning system was going to be. And then So skipping down to the bottom one there, if you could easily write a program by hand, then again, there's no need for you to use machine learning. So one of our engineers at BigML has a story where he wanted to use some natural language processing to do credit card charge type classification. So he wanted to look at where you made a credit card purchase, and he wanted to decide what sort of purchase that was, whether it was a restaurant or a utility bill or groceries or what have you. And so he was very excited about this, and he went and got together a bunch of data with a whole bunch of names of grocery stores and names of restaurants and tried to classify these things. But in fact, it was fairly easy just to do this by hand. So you could program, a bunch of various rules. You look for 10 or 20 keywords in the names of these places, and you could do pretty well classifying the credit card transaction type, just with some simple rules. And so in this case, the expense of gathering this data and labeling all this data far outweighed just sitting down for a half hour and writing a computer program that would do this for you. So again, a place where the traditional expert system model just happens to work very well, and there's no kind of concrete monetary reason to do anything else. And then the last place in the middle there is where the machine learning paradigm kind of breaks down. So if you have data that's difficult to acquire or expensive to label, obviously you don't have enough data to solve the problem if you can't get to it and you can't label it. So medical data is a good example of this. Medical data is usually pretty awesome. Like it's very well curated, and it's usually in a decent format, and it's very informative. Like the people who collect medical data, the doctors who are having the tests run, like it's much cleaner because the consequences of messy data in the medical domain are kind of large, right? You don't want to screw up someone's health, and so the data tends to be very clean relative to other domains. Unfortunately, it's tough to get, right? Because of privacy reasons, hospitals don't, at least in the US, I think here it's a bit better, but in the US, hospitals don't share data, and there's all sorts of privacy requirements. So it's tough to get a nice, consistent data set together because the data is so difficult to acquire. Image labeling is kind of the opposite problem. So if you want to create a classifier that automatically applies labels to images, it's easy to get lots of image data. You can just harvest stuff from the internet, right? There's all sorts of image data on the internet. Unfortunately, applying labels to that data is something that humans usually have to do. So if you have a bunch of pictures of dogs and cats and you want to create a dog or cat classifier, you have to have somebody, there's no way around it, you have to have somebody go through and label cat or dog for each picture before you can train the classifier. And so if you don't have the human labor requirements met there, you don't really have a data set. And then the last thing is rare events. So like when I was working in the stock markets, we wanted to make a classifier that said, is it a time that we basically should not be trading? Is it a time where we should just be out of the markets altogether? Because there were plenty of those times, right? Or seemingly there were plenty of those times. So around like major unemployment numbers, or if Putin invades the Ukraine, these are times we want to be out of the market, right? The problem is that those things only happen, 20 times a year, 30 times a year, 50 times a year. It's a very small number for machine learning, right? It's going to take us 10 years to get together a data set, with just 500 instances. That's not enough. And so with these rare events, things that occur, where you can only get a few hundred data points, it can be difficult to make a machine learning model with so little data. Okay, and the last thing I'm going to talk about here, this is just a little peek under the curtain. So as we start to do machine learning, so now let's say we have the data, we're sure this is a good use case for machine learning. What exactly are we going to do? So this is just kind of a preview of the next few talks. But this kind of, what I'm going to say now is kind of an umbrella over all of the things we're going to say about machine learning algorithms in the next few days. So what's a learning algorithm? A learning algorithm is basically two things, a machine learning algorithm. First of all, it's a space of models that you can learn. So it's a space of possible models that you could use to solve this problem. And then also a clever way of finding the right model that fits your data. So you need both of those two things. You need a space of models, and you need a clever way of searching through it to find a good one, to find one that fits your data. And when I say fits your data, what do I mean? I mean a model that makes predictions on the training data that are consistent with the answers that you know. So just as a more concrete example here, let's think of a simple class of models. So let's say we have a model that picks a feature and just splits the data into two parts based on some threshold on that feature. So we can say, people in our churn data, we can say people who called support and people who didn't, right? That's a simple model. It splits our data into two sets. And let's say if a data point is on one side of the threshold, we're going to predict the majority class of the training data that's on that side. If it's on the other side, we'll pick the majority class of the training data that's on the other side. So basically, the prediction that this model is going to make is going to be the majority class of the set that falls on either side of the threshold. And we'll see a few examples of this. And we can measure how good the fit is on the model by looking at how many of the training data points it gets right after it splits up the data and makes the prediction as the majority class. And then we'll decide the best model is the one where the threshold splits the data so that the predictions are the most right on the training data. So let's see what that looks like on this data. So basically, we have these rows, we have these columns. And if we split the data into two parts based on, let's say, whether or not the person used more than 200 minutes on their mobile phone plan, we get two subsets of data, right? We get the ones that are highlighted in green there, and we get the other ones. And so if we make predictions with this model, you see that the majority class of the highlighted points is no, right? We have 3 no's and 1 yes highlighted. And so if we predict the majority class on that subset, we get that yes one incorrect. So we get one example there, we get incorrect in that subset. And then in the other set here, the non-highlighted points, we have 3 no's and 1 yes. And so again, no is the majority class. We predict no, and we get that yes point wrong for those subsets. So we make 2 mistakes using this model, right? That's how consistent our model is with the training data, is that we make 2 mistakes. That's how good the fit is. So let's try another one. Let's see if they visited the company's website. And that gives us those 3 points highlighted, or those 4 points highlighted, and those other 4 points not highlighted. And you can see we have the same thing. Highlighted points, we have 3 no's and one yes, so we end up getting that yes wrong. And the non-highlighted points, we have 3 no's and 1 yes, so we end up also getting that yes wrong. So we again make 2 mistakes. Now let's see a different one. Let's see people who have spent more than $180 on their last bill. So we have these 3 highlighted points, those 5 points that are unhighlighted, and you can see immediately a difference in the fit, right? The ones that are not highlighted, those are all no's. So we get all of those right if we predict majority class. And similarly, the ones that are highlighted, 2 are yes and 1 is a no, so we only make the 1 mistake. We predict yes and we get the no wrong. And so that's better, right? We've only made 1 mistake. And with these 2 thresholds, we made 2 mistakes. With this threshold, we only make 1 mistake. So this is a better model. And basically, that's all machine learning algorithms are doing, is they're trying different models, they're seeing how well they fit the training data, and depending on how well they fit the training data or where they're making mistakes, they make some update to themselves to make them fit a little better. And that's essentially all machine learning is. I wish there were more to it, because that would mean that I was smarter. But it's not. Machine learning is at its core a very simple thing. It's this process of testing a model against the training data, updating the model so that it fits a little bit better. There are many different ways of doing this, and of course this is kind of a dramatic oversimplification, but it is a useful oversimplification in that that's usually what it boils down to. Okay, so coming to the end of this presentation, there are a couple takeaways here. First of all, when you begin a machine learning project, if you can make that objective of learning concrete, like we did at the very beginning, where we said if we have X% increase in precision, that translates to Y number of dollars. If we can make the objective and the results that concrete, we stand a much better chance of success with our machine learning applications. This is because, again, machine learning is, by its very nature, it only deals with quantities. And so the more precisely you can quantify what you're trying to get out of it, the better off you'll be. And then also, machine learning just isn't the right answer for a lot of problems. And so this is, again, a way to increase your odds of success when you go to deploy machine learning. If you can identify the many situations in which machine learning is the right tool from the situations in which it is not. And kind of a good general piece of advice here is Dijkstra, the great computer scientist, Dijkstra said, before embarking on an ambitious project, try to kill it. So if you can find a reason, to not do an elaborate machine learning solution, you're probably right, because it can be difficult, and often other simpler approaches, if you can find them, will work better. It's only the case where, again, you don't have that expert, you don't have that programmer who can do the job. Those are the cases in which machine learning tends to really pay off. All right, that's the end. Yeah, I can probably take questions later. We should probably move right along because we're running a little bit behind schedule. So thank you very much for listening to me.